Okay, this is the fourth video in chapter 11. I just introduced sp3 hybridization in the previous video. I want to talk more about that because it's the most important hybridization, orbital hybridization, especially in organic chemistry, which we're kind of focusing on. I'm just going to even mention in passing that there are hybrids that actually mix in a fifth and a sixth bonding electron. And what they do is they hybridize not only the S and the P, but they hybridize in either one or two of the D orbitals. And that's how you end up with having 5 bonding electrons or 6 bonding electrons. Now what's interesting about that, and again this is just kind of, you can cover this in the text, and it's not, I don't think it's vital to understand, but the reason why or I should say, if you remember back in chapter 10, you couldn't even have 5 or 6 electron groups unless the central atom was in period 3 or higher, or lower in the periodic table, heavier. And that's because, and I think I mentioned it in passing in chapter 10, is that it requires a d orbital around. Well, the sp3d and the sp3d2 hybridization kind of further illustrates that point, is that in order to have, for example, 6 bonding groups, you need to hybridize the 1s, the 3 p's, and 2 of the d's. And if you hybridize them together, you end up with 6 equal orbitals that are known as sp3d2. And that explains why you're able to have 6 bonding groups or 5 bonding groups. Those hybridizations. That's all I'm going to say about dehybridizations for now. I'm going to go back to sp3. So sp3 again, it's very important. I want to illustrate. I showed the one with carbon. I still have the carbon tetrachloride on the board behind me. I'm going to erase it for a moment and kind of revisit a couple of our other favorite examples with 4 bonding groups. Okay. First one I want to do is good old ammonia. Okay. Now, if you remember ammonia from chapter 10, this is one of these AX3Es, because from a Lewis standpoint, it's NH, H, H, and a lone pair. Okay. Now, let's look at this from an orbital standpoint. From an orbital standpoint, we got to look at nitrogen. Nitrogen has again a 2s and all these p's, 3 p's, okay? And there's 5 electrons in the atomic state. So in the atomic orbitals, they look like 1, 2, 3, 4, 5, okay? Now, what happens to form ammonia? You'd think that, why? It seems like what could happen here is that the p orbitals could just be used, since they're all half filled, with hydrogen, and then just leave this lone pair as an S. Doesn't work that way. And that's about all I'll say at the moment. What actually happens is that these orbitals hybridize. And they hybridize to form the 4 sp3s. And then nitrogen fills the 5 electrons. 1, 2, 3, 4, 5. These are now the electron groups that end up bonding. The 3 that are half filled each bond with one of the hydrogens, and the sp3 orbital that is filled is essentially this guy, the lone pair. Okay. Now, the reason why this is preferable over having the 2 sp paired has to do with geometry. It turns out this lone pair group, by measurement, we know that this lone pair group is kind of shaped with respect to the other bonds. It's kind of shaped like a tetrahedral. And if this lone pair instead were a 2s orbital, it would be shaped as a sphere around the center, which doesn't really make sense. It doesn't actually match with our observation of how this lone pair kind of behaves. So the hybridization of sp3 makes much more sense in explaining the geometry that we observe in ammonia. One more example along those lines is water. O. We know this is an AX2E2. And what that means is we have two pairs, two lone pairs on oxygen. We know that molecule is a bent molecule. We know it's highly polar, of course. Okay. The central atom in this case is oxygen. Oxygen has the same sort of orbitals here that nitrogen had, but it actually has 6 electrons, so its atomic orbitals kind of look like this. But when these hybridize, we end up with 4 orbitals in the sp3, 6 electrons, so it goes 1, 2, 3, 4, 5, 6. And that matches the shape here. These 2 orbitals that are filled are the 2 lone pairs, and the 2 orbitals that are left over are bond with the hydrogen. Okay. Okay. So I think you got a feel for what sp3 looks like. I wonder if I have enough time to get this one in. I bet I don't. I'm going to end this one. It's a short little video. I'll end this, and I'm going to cover the last concept of VB theory in the next video.